In this lesson, we'll look at the phenomenon of turbulence and how it is created within the atmosphere. More importantly, we'll examine its impact on aviation and how we can locate it and avoid it. Turbulence strictly means a disturbed state, but in aviation, it means disturbed or rough air. For the purpose of a definition, we will consider turbulence to be variations in the wind along the aircraft's flight path, of a pattern, intensity and duration that disturb the aircraft's attitude about its major axes, but do not significantly alter its flight path. To simplify this statement, we can say that turbulence does disturb the aircraft's attitude, but the aircraft can still maintain its flight path. Wind shear is similar to turbulence, but far more severe. It is not rough air, but air that has marked variations in speed and/or direction. A definition of wind shear is variations in the wind's speed and direction along an aircraft's flight path of a pattern, intensity and duration that displace the aircraft abruptly from its intended path, such that substantial control action is required. Strictly speaking, wind shear is a rate of change of the wind velocity in space, and is to be considered a vector. Vertical wind shear is the change in the wind speed and/or direction with height. The diagram shows what this might look like. The bottom of the tower is exposed to a very different speed and direction than the top. Vertical wind shear is usually measured in knots per 100 feet. Horizontal wind shear is the change in the wind speed and direction with horizontal distance. Again, the diagram shows this using a runway to illustrate the situation. The direction and speed at one end of the runway is very different to that at the other end of the runway. Horizontal wind shear is usually measured using knots per 1,000 feet. We will discuss wind shear later in the lesson, but for now let's return to turbulence, which was disturbed or rough air. One of the most common causes of turbulence is the surface over which the airflow is moving. The layer of air that is disturbed is known as the friction layer. Above this, the airflow is unaffected by the surface. The boundary of the disturbed surface flow and the undisturbed upper flow is called the friction level. This disturbed air near the surface is created in two ways. Mechanically, by objects like trees, hills and buildings, and thermally, through the effect of warm air rising. We call these effects mechanical or thermal turbulence, respectively. If we first look at mechanical turbulence, we can see that the greater the physical obstruction, the greater the depth of airflow that is disturbed. This is common over land, especially around hills and towns. Notice that the friction layer is thicker and that the friction level is higher. Thermal turbulence is slightly different though. Some areas of the Earth's surface will be warmer than others, and will have greater amounts of warm air rising above them. This again acts as a disturbance to horizontally moving airflow. Notice also that the greater the thermal currents, the thicker the friction layer, and the higher the friction level. This would be common with areas of low albedo, like rocky areas and fields, where the surface is absorbing large amounts of solar radiation. This thermal effect is extremely important to glider pilots, and they will examine the land carefully, not only for physical objects giving vertical currents, but more importantly for areas giving marked thermal up currents. As a result of the thermal effect, we should be able to notice a diurnal change in the friction layer and the friction level. When the land is at its coldest, usually just after sunrise, the friction level will be at its lowest, whereas during the afternoon, when the land is at its warmest, the friction level will be higher. However, on average, the depth of the friction layer is only a few thousand feet above the surface, usually 2,000 to 3,000 feet. But as we have seen, this will vary. It is not just near the surface where we find disturbed air. A very common place is within and surrounding significant cloud developments. Looking at the diagram, we know that the cloud was created by air rising and cooling. Within the cloud, we can see significant vertical currents of air. These will disturb the general horizontal flow of air, creating turbulence. Clouds therefore present to the pilot a very good visual clue to the movement of air and the potential hazard. For this reason, cumuliform clouds, which are vertically developed clouds, are treated with caution in aviation. Cumulonimbus clouds are the most visually obvious in terms of their turbulence capability, and turbulence around these clouds is always severe. A fact not commonly emphasized to pilots is that we don't just find turbulence within the clouds themselves. Looking at the diagram, we can see the turbulent currents close to the areas of cloud development. However, turbulence from these systems can still be experienced at some distance from the cloud development. If we now consider the bigger picture, we can identify downdrafts at quite some distance from the cloud. These currents can also cause turbulence, and again, very large cloud development, like cumulonimbus, must be treated with extra caution. There is one added concern with large cloud developments, particularly the cumuliform type. When precipitation falls from clouds, it tends to drag air down with it, creating downdrafts within and underneath the cloud. This situation will aggravate any turbulence created already from the rising air, since now we have air going down as well as up. If the amount of air descending from the cloud is significant enough, then a phenomenon known as a microburst or macroburst is experienced. In some countries, these are sometimes called cloudbursts. These will be discussed in detail in the lesson on thunderstorms, but suffice to say, these present a major hazard to aviation. When the air descends beneath the cloud, it may come into contact with the ground and then spread out. Because of the very large changes in the direction and speed of the wind, both vertically and horizontally, this gives rise to very dangerous wind shear. There are many causes of wind shear in the atmosphere. In fact, whenever a pilot sees evidence of an abrupt change in wind speed or direction, he should expect to encounter the effects of wind shear, for example, around surface troughs or ridges, particularly those associated with fronts. In the diagram, we can see a location in the northern hemisphere, which is about to experience the passage of an active cold front. The initial wind direction is from the southwest, but as the front passes, the wind direction changes quite rapidly to flow from the northwest. This rapid change in direction will lead to wind shear, and pilots need to be aware of changing wind conditions with the passage of active fronts. We also find significant troughs and ridges in the upper atmosphere. Here, although the winds tend to blow parallel to the isobars, once again, when looking along the trough, we can see substantial changes in direction. However, unlike the cold front near the surface, these areas seldom have the visual clue of clouds to aid the pilot. As a result, these areas of turbulence are called clear air turbulence, or CAT for short. There is one very significant place where clear air turbulence can be found. In the upper atmosphere, we have narrow bands of fast-moving air called jet streams. The speed of these jets of air is frequently between 100 and 200 knots, and can reach 400 knots in rare circumstances. The turbulence or wind shear is not within the jets themselves, but rather around their edge. Surrounding the edge is a zone where the speed changes very rapidly across a short distance, causing extensive turbulence. On the diagram, we can see a cross-section of a typical jet stream. Notice the jet itself is located within the warm air, and the clear air turbulence is located to the side of the jet that faces the cooler of the air masses. The black lines are isotachs, which are lines joining places of equal wind speed. Notice the speed in the centre, and more importantly, notice how close the isotachs are on the cold side of the jet. This shows the rapid change in speed, and is where the clear air turbulence is most likely to be found. These areas are very important to aircraft operating at high altitudes, and as such are shown on significant weather charts issued to aircraft operators. This is an example of a chart showing a CAT area surrounding a jet stream. These charts will be discussed and examined later in the weather briefing section, under medium and high-level significant weather charts.